Hello everyone. I'm very pleased to be here today and to be part of this special session on a topic that has been inspiring me for several years now. So today I will be presenting a paper that examines and demonstrates the importance of the model age at death in longevity research. I'll be doing so on the behalf of our team, the M team. This is not working. Oh, maybe not. Sorry for the interruption. I just missed my punch. Okay, so I guess I won't go with this.
You may use the arrows actually.
Yeah, I'll use the arrows. Okay, so as I was saying, I will be doing this presentation on the behalf of our team that we call the M team. M, of course, stands for the model age at death. So you've heard Jean-Marie talk just a few minutes, give a great talk on disability-free life expectancy. There's also Shiro Oriushi from the City University of New York, Sulan Karen Chung from the University of Hong Kong, and myself. So we're very much looking forward to your comments and questions, and in order to leave enough time for that, let's begin. So the mankind witnessed a substantial increase in the length of human life during the last 2 centuries. In countries that currently have relatively low levels of mortality, life expectancy at birth for both sexes rose from around 30 or 40-ish years in the mid-19th century to about 80 years in recent periods. This longevity expansion resulted in a considerable growth of the elderly population. It also led to increasing concern about inequalities in the length of life among different populations and different subpopulations. So in order to monitor and to analyze these longevity trends and differentials, we need to use proper and effective summarizations of statistical data on human lifespan. Now, in terms of the length of survival time, there are three major types of measures of the overall lifespan, and these are the mean, the median, and the mode of the length of life distribution. In other words, the life expectancy at birth, or E0, the median age at death, and the model age at death, which I will refer to as M in this talk. So E0 has been widely used, we all know that, but increasing attention has recently been given to M. So you may be wondering, what are the features of M that makes it a special, or that gives it a special significance for longevity research? Well, just by looking at this age distribution of deaths for French females, you can see that M, shown in turquoise, represents the death heap in old age. If this distribution of deaths for French females was perfectly symmetrical, both the life expectancy at birth and the median age at death would be equal to the mode, and all three summary measures would be representative of the location of this death heap, so the peak in the distribution. But we know that the age distribution of deaths among humans is highly skewed to the left, and therefore the model age at death is considerably older than the life expectancy at birth, and the median age at death is placed between them. This hierarchy between the three measures always holds in human mortality because, unlike the life expectancy at birth and the median age at death, the mode, M, is exclusively influenced by old age mortality, as long as the mortality profile follows a bathtub shape. So in order to make this statement clearer, the fact that M is determined exclusively by old age mortality, we're presenting here some kind of a toy example or empirical example to make this more clear. So as you can see on this figure, we forced all three life tables to have the same death rates above age 70 and to have different death rates below this age. The death distribution that corresponds to these three mortality schedules are given here on the right-hand side. And note, just to make these comparisons easier, we forced the number of deaths between age 75 and 76 to be equal to 1 in all three life tables. So, although the death distributions under the age of 75 are different, the age distributions above 75 are all the same, and therefore the most typical age at death is 84 years in all three life tables. So in this example, M, the model age at death, is determined by mortality at ages 75 and older, and regardless of mortality under age 75. So in the paper, we also developed a line of mathematical reasoning to show that M is exclusively determined by old age mortality, if that interests you. We'll be happy to share that with you. So due to M's special features, its past trends were noticeably different than those for E0 and the median age at death. And this is what the figure shows. This is the case of France, but very similar patterns were observed for other several high-income countries. In the first half of the 20th century, you can see that the life expectancy at birth in purple and the median age at death in gray were increasing quite strongly, but the trajectories of the model age at death were either flat for males or increasing, but only slightly for females. Then, after that, the life expectancy at birth and the median age at death tend to slow down, and this is where the mode actually picks up and starts to rise. It started to rise among females first, around 1945 about, and for males not before 1970. All right. So these different trends for the three indicators bring me to our main research questions. So in the existing literature on the model age at death, we feel that there are at least two questions that remain unanswered. The first one is empirically oriented. So the questions that we've asked ourselves is, could patterns of trends in the model age at death be noticeably different from those in widely used measures of old age survival, such as E65? So if this is the case, if the trends in M and the trends in E65 are different, then maybe M may be able to shed light on some aspects of mortality trends that are not captured well by E65. We already saw in the previous slides that trends in M and trends in E0 were quite different, but how about those for life expectancy at an older age, like E65 or even E55 or E75, for instance? Our second question is theoretically oriented. It is well known that some mathematical equations like the Gompertz, logistic, Weibull models fit empirical variations of adult mortality quite well. These equations are often used in mortality studies, in aging research, in population projections, in simulation studies, and so on. So could these models be reformulated using M as their key parameter? And if yes, are there any advantages in doing so? And what role does M exactly play in these reformulated equations? All right, so in order to address these questions, we rely on data for the French civilian populations that are available on the Human Mortality Database. To estimate the model age at death, we use a method for deriving M from the Poisson peace-spline smooth mortality curve. This method to estimate M was actually developed as part of my PhD dissertation. If you'd like to know more about that, we can talk after this session. So why do we need smoothing? Well, on the left-hand side here you see that without any smoothing, the typical flatness and somehow irregular pattern in the model age at death area makes it quite difficult to identify with great precision the model age at death value, but with smoothed curves then it becomes quite easy to identify them. Alright, the results. So let's start by looking at end trends and comparisons with old age life expectancies, E55, 65, and E75. So life expectancy at a given old age is, of course, not influenced by mortality before the age for which we compute the life expectancy. So for instance, E65 is only influenced by mortality at ages 65 and above, not by mortality below age 65, because in principle everybody has to survive in order to participate to E65. Therefore, it may seem reasonable to expect quite similar trends in M and in life expectancy at an older age. But in fact, it's not the case. As this figure shows, the rises in M, so this is the turquoise line, tend to be steeper than rises in life expectancy at age 55, 65, and 75. We also notice that the older the life expectancy is, the slower is the increase. So for instance, E75 in pale blue, E75, for instance, has a slower pace of increase compared to E65, which in turn has a slower pace of increase than E55. So this reflects the fact that changes in life expectancy at an old age are highly age dependent. So whether you choose E55, and if your neighbor chooses E65, you might not get the same conclusions in terms of changes in these high life expectancy at high ages. Changes in M are absolutely not age dependent. So this is truly an advantage. So in order to understand these different trends better, and also to make sure that what we're observing here is not some kind of peculiarities to the French mortality history, we ran a simple simulation of an old age mortality shift. So for a hypothetical population, we assume that adult mortality shifts by 1 year of age in every 4 calendar years. And the results of this simulation exercise showed that M increased from age 65 till age 90 in 60 years, 60 simulated years, therefore capturing exactly the mortality shift that this simulation was imputed with. Old age life expectancy, on the other hand, increased more slowly. Therefore, mortality shifts are more accurately captured by the model age at death than by any of these old age mortality or old age life expectancy. So this can be mathematically proven to make it more general. The proof is included in the paper, and I've included it here just to show you that actually it's quite a simple proof, but no one had thought of it earlier. Alright, the last few slides are about M and mathematical models of mortality. So conventionally, the force of mortality at age X in the Gompertz, logistic, and Weibo models are expressed as these. These models can, in fact, be reformulated using M, so that was one of our questions, and yes, it's possible. And the reformulated equations look like this. Note that in all of these new expressions, parameter A has been replaced by parameter M, so the re-expressions depend on two parameters M and B, whereas the conventional one depends on A and B. For what we know, this special advantage of the model age at death has not been found for E0 or the median age at death or any old age life expectancy. although the reformulated equation may seem to you slightly more complicated than the conventional forms, what I would say is that m as a parameter in the re-expression has a more intuitive, or I would say it's more clearly interpretable than parameter a in the conventional form. And I'm illustrating that. I have 2 slides left. So for instance, in this figure, we fitted the Gompertz model to death rates in 1965 and 2005. This is still French data for males. And we fitted the models from age 60 to age 90. We estimated the parameter A, which is shown, and the estimated value is shown by an asterisk here. And the estimated value of the model age at death is shown by a dark filled circle. In the Gompertz model, A is the force of mortality at age 0, and therefore it is extrapolated from adult ages. And this is the extrapolation that is shown here on this figure. Therefore, A is a highly hypothetical quantity, I would say, and its interpretation is not as straightforward as M. For instance, if you compare actual values of the central death rate at age 0, the values in 1965 and 2005 are actually quite different than what you obtained for the parameter A. So that's an issue. Moreover, the values estimated for the A parameter are so small that it's kind of difficult to understand really, or to have a clear illustration of what it means, or intuitive understanding of those very small values. On the contrary, the meaning of M is very clear. So to wrap this up, what are the take-home messages? First, as a summary measure of lifespan that reflects mortality rates at all ages, so from birth till the very, very old ages, E0 should remain to be a main demographic indicator. However, in the era in which we currently are living, in the era in which the length of the human life is extending mainly because of reductions in old age mortality, it is also very useful to have an indicator, a lifespan, an additional lifespan indicator that has a special focus on old age survival. M is our candidate, the candidate we're pushing for, and we therefore strongly recommend that M should be included in the standard set of indicators and widely used in longevity research. Thank you for your attention.
In the list of models, you didn't include MAKEMs. Is
Yes.
it possible to rewrite it in terms of them?
Good question. In the paper, we do show the conventional forms of the MAKEM model for all 3 models and the reformulated equations, and it works equally as well. Yes. So it's very important if you're planning on including younger ages, including the MAKEM.
Suppose age at death, singular age at death,
Yes.
requiring singular input, singular age at death. If I don't have the singular age at death in my country, if I get the grouped data, so then can I transform these group data into singular data by some multipliers like some other Beer's multiplier, some other multipliers? I have myself exercised this, but when applying this model age at death on the pattern of singular age data obtained from the group data,
Yes.
I didn't get the model age at death properly, because
Yes.
I am getting some formula for model age at death on the basis of Gompertz model. So I found the formula for this model age, and I put the data, singular age data, by transforming from the group data, but I couldn't get the proper answer. So what is the fallacy of that? And you are making some smoothness of the data by spline and all these things.
Yeah, yeah.
So I think that if multipliers are used, Sprague multipliers, suppose. So Sprague multipliers, if I use in the group data, automatically the data, single layer data will be more smooth itself, because this is a formula which is itself smooth.
Yeah.
So then formula what is my question is this, that how to get this single layer edge data, not raw data, because we don't have
You
this.
don't have.
This raw data, but group data we have. But from the group data, can I obtain this single layer data by using like tables? We are using this Sprague multipliers or Beers or boards like this. So in this case, can you use these multipliers and apply this formula for modal edge data?
So, okay, so many things here to say. First, yes, all of this that I've presented is based on single year data, the data that you don't have.
Yes.
You're not the only one with only aggregated data. I guess you have 5-year age groups, something like that. The method that we've used here, the P-spline method that we've used, is for single year of age data. If you have aggregated data, you would have to modify a little bit the smoothing method, but I think it would be more satisfying to go with that than to estimate the single year age data with a parametric model. I think it gives you more flexibility. We could be in touch, because this is something that I've been wanting to work on using, I guess, in the statistical literature, you have a lot of work that's been done on P-splines with bin data, like in aggregated age group, finally. I'm just not sure how it would work on mortality data, if it works well, and what you would get as an outcome for the model age at death. Would you get something that is interesting or not? And the way to test this is to use a country that has single year of age data, pool it to get age groups, and compare the model age at death that you get with both approaches to see if it's satisfying or not. Yeah.
Thank you.
Thank you very much.